Hi dear students, this particular class we are going to introduce the limit idea and try to discuss all the concepts related to the limits. Okay, so this is the particular question given. F of x is equals to x square minus 9 divided by x minus 3 if x is not equals to 3. Because when x is equals to 3, no doubt that function is not defined. So now I can write this function as x plus 3. F of x is equals to x plus 3. Let us say that is equals to y. I am trying to draw the graph for that. So this is the line y is equals to x plus 3 line. This particular line, because you can observe when x is equal to 0, you will get y is equals to 3. This is the particular point 0 comma 3. At the same time, when y is equals to 0, you will get x is equals to minus 3. So minus 3 comma 0. Now the straight line is passing through 0 comma 3 and minus 3 comma 0. This is the straight line. So at 3, this function is not defined. This is the corresponding value of x. X is equals to 3, whereas here the corresponding value is 6. That means 0 comma 6. Right? Now observe the graph, especially when x values are approaching to 3 from left hand side. That means x values are very close to 3 to the left of 3. X values are very close to 3. That's what we can write it as when x values are approaching to 3 from left hand side. 3 minus denotes it is not minus 3. X values are approaching to 3 from left hand side. So when x values are approaching to 3 from left hand side, you can observe the graph. The graphical values are approaching to 6. F of x values are approaching to 6. At the same time, when x values are approaching to 3 from right hand side, you can observe in the neighborhood of 3. In the neighborhood of 3 means very close to 3 in the left hand side and the right hand side. That's what we can write in this way. 3 minus delta, 3 plus delta. This is called in the neighborhood of 3. That means very close to 3 in the left and right side. So that's why when x values are approaches to 3 from right hand side in the neighborhood of 3, that's what we can write. When x values are approaching to 3 from right hand side, functional values are approaching to 6. The same definition we can write in this way also. Modulus of x minus 3 less than delta. What is the meaning for this? 3 minus delta less than x less than 3 plus delta. When x values are there in the deleted neighborhood of 3, that means in and around 3. Yet 3 it is not defined. That's why in the deleted neighborhood of 3. So when x values are present in between 3 minus lambda delta and 3 plus delta, then f of x values present in the in and around 6, that we can write it as f of x minus 6 less than epsilon. That's what we can write it as f of x lies between 6 minus epsilon and 6 plus epsilon. That is, we can discuss as epsilon delta definition for limit. It is nothing but the same meaning. When x values are approaching to 3 from left hand side, functional value is approaching to 6. When x values are approaching to 3 from right hand side, functional values are approaching to 6. That's what we can write in this way. Limit x tends to 3 minus f of x value is approaching to 6. Limit x tends to 3 plus f of x value is also approaching to 6. That means whenever the left hand limit and right hand limit, which we will call it as a left hand limit and this one we will call it as a right hand limit. So whenever the left hand limit and right hand limit are equal, then we say that limit x tends to 3 f of x is equals to 6. So in this particular case, limit x tends to 3 f of x is equal to 6 means this one. So whenever x values lies between 3 minus delta and 3 plus delta, where delta is very greater than 0, very small. Whenever x values are there in the deleted neighborhood of 3, then f of x values are there in the neighborhood of 6. So that is about the definition of a limit. Limit x tends to 3 f of x is equals to 6 we can write. So let's take another example here. I am discussing the function here as f of x is equals to mod x by x. This function also, whether you observed or not defined at x is equals to 0. Now I can write this function as 1 if x greater than 0. F of x is equals to mod x by x if x not equals to 0. So that we are writing it as 1 if x greater than 0, and we can write minus 1 if x less than 0. That means when x is equal to 0, it is not defined. So we can write that function in this way. Graph of that function we can draw like this. When x values are 0, more than 0, we are getting 1. When x values are less than 0, we are getting minus 1. So this is the line y is equal to minus 1, and this is the line y is equals to 1. Now this is 0. You can observe in the right neighborhood of 0, the functional values are approaching to 1. In the left neighborhood of 0, the functional values are approaching to minus 1. That's what we can write in this way. Limit x tends to 0 minus f of x. When x values are approaching to 0 from left hand side, functional value is equal to minus 1. Similarly, when x values are approaching to 0 from right hand side, functional value is equals to 1. Whether you observed or not, left hand limit is not equals to right hand limit. So we can say limit x tends to 0 f of x does not exist. Does not exist, we are saying. So that means when can we say that limit exists? Limit of a function exists only when left hand limit must be equal to right hand limit. Observe here one particular case I am discussing. I hope so everyone is familiar with the greatest two integer function, integral part of x. Now at x is equals to 5. That means I am asking limit x tends to 5 integral part of x, or at the same time limit x tends to 5 by 2 integral part of x. Now you can observe here limit x tends to 5 minus integral part of x we have to find out. Limit x tends to 5 plus integral part of x we have to find out. Left hand limit, right hand limit, both we have to find out. Now here limit x tends to 5. Come on, tell me. 5 minus means less than 5. Less than 5 means 4.999. So that means when x values are less than 5, when x value is equal to 4.999, integral part becomes 4. That's why this value of the limit is equals to 4. Next here, limit x tends to 5. 5 plus, that means 5.00001. Integral part becomes 5. So that value we are getting 5. So left hand limit is not equals to right hand limit. So we can say the function is limit does not exist at x is equals to 5. But observe here, in this case we can check here. Limit x tends to 2.5 minus integral part of x. And here what happens? 2.5 minus 2.5 minus means 2.4999. So that's why that value is also equal to 2 only. 2.4999. So that's why here also limit x tends to 2.5 plus integral part of x. Here 2.5 plus means what happened? 2.5001. In that case also this integral part is becoming 2 only. So left hand limit, right hand limit both are equal. So I can say this limit value is equals to 2. So that's why greatest integer function limit does not exist at all integers. At all, not only at 5, you can take any integer. Greatest integer function limit does not exist. So whereas here limit exists. I hope so everyone know about this particular idea. A to the power of n, when the value of a is more than 1, a power when a greater than 1, a power n. As n tends to infinity, a power n is also tending to infinity. But as n tends to minus infinity, or n is tending to minus infinity, so this value 1 by a whole to the power of n. That means a power n, when n is tending to minus infinity, suppose you see 2 power minus, it is nothing but 1 by 2 whole power. Yes or no? So this value is less than 1. When it is less than 1, this total value is approaching to 0. That's why n tends to infinity, a power n tends to infinity. When n tends to minus infinity, a to the power of n tends to 0. So this particular information I hope so everyone know. When a greater than 1, n tends to infinity means a power n tends to infinity. N tends to minus infinity, then a power n tends to 0. So at the same time, the other way of approaching this one, this is the actual definition we discussed. Limit x tends to a minus f of x is equals to limit x tends to a plus f of x. If both are equal and equal to L, then we written limit x tends to a f of x is equals to L. Left hand limit is equals to right hand limit, that must be equals to L. Then we can say that the value of this limit is equals to L. Now my question is here, x tends to a minus. A minus means from a small value we are subtracting. So that subtracting value I am taking it as h. What I am doing, in place of x I am writing a minus h. From a I am removing small value, subtracting small value, where that is very close to 0. H is tending to 0. That's why wherever x is there, in place of x we can replace a minus h, and in place of this x tends to a minus, we can write h tends to 0. In the similar way, x is equal to a plus, you can replace with a plus h, and x tends to a plus, we can write it as h tends to 0. So observe that I am writing here limit h tends to 0, f of a minus h is equals to limit h tends to 0, f of a plus h. This is the other way of representing the same limit. Okay, nothing I did. X tends to a minus. From a we are removing small value, that removed the value very close to 0. Here also for a small value added, very close to 0 value added. So that's why this way also we can represent the limit. Now you can observe another question here. The question is given in this way. Limit x tends to 0, e to the power of 1 by x minus 1 divided by e to the power of 1 by x plus 1. We want to find out that limit. So here what I am doing is, this can be written as limit x tends to 0 minus, we have to find out and also we have to find out limit x tends to 0 plus f of x also. Let's see the first case. This can be written as, according to earlier discussion, limit h tends to 0, e to the power of minus 1 by h minus 1 divided by e to the power of minus 1 by h plus 1. Now whenever h is tending to 0, that means e power minus infinity. So e value 2.718, e value 2.718, more than 1, power is tending to minus infinity. So e power minus infinity, that value is tending to 0. That's why you will get this one as 0 minus 1 divided by 0 plus 1, that is equals to minus 1. Whereas here what happens? This is equals to limit h tends to 0, e to the power of 1 by h minus 1 divided by e to the power of 1 by h plus 1. What happens here? So here numerator is also tending to infinity, denominator is also tending to infinity. We are getting infinity by infinity. Don't say infinity cancel, sir. We will get 1. It is an indeterminate form. Okay, whenever we are getting infinity by infinity, we have to do the modification. This is the modification I am doing. Limit h tends to 0, 1 minus e to the power of minus 1 by h divided by 1 plus e to the power of minus 1 by h. Now you can observe this limit value is tending to 0. This is also tending to 0. So that's why we are getting 1 minus 0 divided by 1 plus 0, that is equals to 1. So we got left hand limit is equals to minus 1, right hand limit is equal to plus 1. Both are not equal. So we can say limit of this function does not exist. Right? So that is the discussion regarding the basic idea of the limits. Suppose I want to discuss a few operations on limits. These are the basic operations. Limit x tends to a, f of x plus or minus g of x. We can write it as separately. We can apply the limit. Limit x tends to a, f of x plus or minus limit x tends to a, g of x. Next one we have limit x tends to a, f of x into g of x. We can apply the limit separately. Limit x tends to a, f of x into limit x tends to a, g of x. Next we have limit x tends to a, f of x divided by g of x. We can write this one as limit x tends to a, f of x divided by limit x tends to a, g of x, provided denominator, that means limit x tends to a, g of x value not equals to 0. At the same time, limit x tends to a, lambda into f of x, where lambda is a scalar. We can write that one as limit x tends to a into f of x. So the other discussion here only we can do like this. Limit x tends to a, f of x whole to the power of g of x. We can write this one as limit x tends to a, f of x whole to the power of limit x tends to a, g of x, provided both the limits are finite limits. That means this value is equals to L, this value is equals to M. Both are finite values. So then we can write L power M. So another discussion here that we will call it as sandwich theorem. So what is sandwich theorem? In the deleted neighborhood of A, f of x value less than or equals to g of x, which is less than or equals to h of x. In the deleted neighborhood of A, f of x less than or equals to g of x less than or equal to h of x, and limit x tends to a, f of x is equals to L, limit x tends to a, h of x is equals to L. That means this limit value is equals to L and this limit value is also equal to L. So in the deleted neighborhood of A, very close to A, this functional inequality satisfies. Then we can write limit x tends to A, g of x is also equal to L. That is called sandwich theorem. Right? So that is the discussion regarding few operations on limits. Now you can observe here, whenever we are getting 0 by 0 form or we are getting infinity by infinity form, 0 into infinity, right? And at the same time 0 power 0 and 1 power infinity, these are all called the indeterminate forms. 0 into infinity, 0 into a finite value we can write 0, but 0 into infinite value you can't write 0. So these are some indeterminate forms. In case of these indeterminate forms, we have to take care while solving the limits. So next discussion here we are going to do some standard limits formulas I will try to discuss. The first formula is limit x tends to A, x to the power of n minus a to the power of n divided by x minus a is equals to n into a to the power of n minus 1. So we are trying to prove this one. This is equals to limit x tends to a plus x power n minus a to the power of n divided by x minus a. That we can write it as limit h tends to 0 a plus h whole to the power of n minus a to the power of n divided by a plus h minus a. Now what we are doing here, this can be written as limit h tends to 0, take a common, then we will get a to the power of n into 1 plus h by a whole to the power of n minus 1. Yes or no? Divided by h. So from here I taken a common, a will come outside as like this minus 1. Okay. So now this a power n does not depend on the limit. That's why we can write outside this is equals to a to the power of n into limit h tends to 0 1 plus h by a whole to the power of n minus 1 divided by h. I hope so everyone know the expansion of 1 plus x whole to the power of n. 1 plus x whole to the power of n expansion is 1 plus nx plus n into n minus 1 divided by 2 factorial into x square plus and so on. So now expand that one. So we can write that one as a to the power of n into limit h tends to 0. So 1 plus n into h by a plus n into n minus 1 divided by 2 factorial into h square by a square plus and so on, right? That is the expansion of that particular idea, minus 1 divided by h. Here plus 1, here minus 1 cancel. You can observe from all the remaining terms we can take h common, that h cancel with the denominator h. Then what left? That is equals to a to the power of n into limit h tends to 0, h cancel, we are getting in the first term n by a plus n into n minus 1 divided by 2 factorial into h by a square plus and so on. So now here in every term there is an involvement of h, it becomes 0. So we are getting a to the power of n into n by a. So that is nothing but n into a to the power of n minus 1. So limit x tends to a, x power n minus a to the power of n is equals x power n minus a power n divided by x minus a is equals to n into a to the power of n minus 1. So next, I hope so this one you know, limit theta tends to 0, sin theta we can write it as 0, and at the same time limit theta tends to 0, cos theta is equals to 1. Direct limit substitution, cos 0 is equals to 1. But now tell me, limit theta tends to 0, sin theta by theta, very important result, sin theta by theta is equals to 1. That I am going to prove with the help of sandwich theorem. Observe here. Let us take a circle. This is the circle whose radius is equals to r. This is the center of the circle. Now this is the radius. I am assuming that radius is equals to r. So here a tangent is drawn. So from the center of the circle we join the tangent. Let us take this point as B and this particular point as A, and this is equal to say some C. Now you are observing three types of figures here. One is a triangle OAC, one is a triangle OAC, OC is also the radius. I am taking this measure of this angle is equals to theta, theta is measured in radians, and OAC is a sector also, and again OAB is a triangle. Now observe there, I hope so this is the one particular information you have to know from the properties of triangles chapter. This angle is equals to A, and this is C, and this side is B. Then area of this triangle is given by half into BC into sin A. Area of the triangle is equals to half into BC into sin A. That is the area of a triangle. This particular information you have to know, that I am going to use here. Now area of a triangle OAC, triangle area OAC is less than or equals to area of a sector OAC, sector area OAC, which is less than or equals to area of a triangle OAB. So what is the area of a triangle OAC? According to the earlier discussion, half into r into angle between them is sin theta is less than or equals to, you know, the area of a sector. Sector area is equals to LR by 2, where L is equals to r theta. That's why area of the sector is equals to r square theta by 2 is less than or equals to area of a triangle OAB, half into base is equals to r, height is equals to AB. Now tell me from this triangle, what is tan theta? Tan theta is equals to AB divided by r. So I can write AB is equals to r tan theta. So in place of AB I am writing r tan theta. You can observe throughout the inequality r square by 2 cancel or not. So cancel that r square by 2. Then we are getting sin theta is less than or equals to, come on, theta is less than or equals to tan theta. So we are discussing limit theta tends to 0. That means theta is very close to 0. When theta is very close to 0, sin theta is positive, right? But when sin theta is positive, what can we say? Sin theta is positive, what we can say? So that's why positive we can divide. 1 less than or equals to theta by sin theta is less than or equals to cos theta. Now reverse the inequality, 1 by cos theta, right? We are dividing with the sin theta. So you will get 1 by cos theta. Now I can write this one as cos theta less than or equals to sin theta by theta is less than or equals to 1. Now as limit theta tends to 0, cos theta is less than or equals to limit theta tends to 0, sin theta by theta is less than or equals to limit theta tends to 0, 1. So we know this limit value is equals to 1. We know this limit value is also equals to 1. So according to the sandwich theorem, we can write limit theta tends to 0. Limit theta tends to 0. Sin theta by theta, we can write it as 1. Right? So based on this application, we can write limit theta tends to 0, sin theta by theta is equals to 1. Not only limit theta tends to 0, sin theta by theta. Limit theta tends to 0, theta by sin theta, we can also write it as 1. At the same time, limit theta tends to 0, tan theta by theta, also we can write 1. The reason is limit theta tends to 0, tan theta can be written as sin theta by theta into 1 by cos theta, right? Sin theta by theta is equals to 1. If you substitute here, cos 0 is equals to 1. So this is the value. At the same time, limit x tends to 0, sin inverse x divided by x, also we can write 1, whereas limit x tends to 0, tan inverse x by x, we can write 1. The reason is, you can see here I am taking x is equals to sin theta. Whenever we are taking x is equal to sin theta, that theta, whenever x is tending to 0, theta is tending to 0. That's why that question changes as theta tends to 0. In place of sin inverse x, we have to write theta, divided by in place of x, we have to write sin theta. As we discussed, theta by sin theta is equals to 1. So that's why limit x tends to 0, sin inverse x by x is equals to 1, tan inverse x by x is equals to 1, x by tan inverse x also 1, x by sin inverse x is also equal to 1. So this is one more formula better to remember for the purpose of objective exams. Limit x tends to 0, 1 minus cos ax divided by x square is equals to, we can write a square divided by 2. So how we are getting this particular formula? You can observe here. You know very well, limit x tends to 0, 1 minus cos theta, we can write it as 2 sin square theta by 2. 1 minus cos theta, we can write it as 2 sin square theta by 2. Now what I am doing, observe here, x square is there, that I written in here x. Now multiply with a by 2, definitely we have to divide with a by 2. Multiplied with a by 2, here also multiplied with a by 2. Numerator multiplied with a by 2 whole square, denominator multiplied with a by 2 whole square. Now you can observe it is in the form of sin theta by theta. Sin theta by theta, this theta is also tending to 0. The reason is x is tending to 0, x is tending to 0 means ax is also tending to 0, ax by 2 is also tending to 0. That's why sin theta by theta, theta is tending to 0, this value becomes 1, 2 into a square by 4, so you will get the answer as a square divided by 2. So that is the way we can remember. Limit x tends to 0, 1 minus cos ax divided by x square is equal to a square divided by 2. Sir, what happens, sir, if I apply direct limit? Observe here, if you apply the direct limit, what happens? Cos 0 is equals to 1. 1 minus 1, we are getting 0 by 0. So we are getting 0 by 0 form. Whenever we are getting a 0 by 0 form, we can apply L'Hospital rule. L'Hospital rule. So what is L'Hospital rule? Whenever we are getting a 0 by 0 form, we can apply for L'Hospital rule. So what to do in L'Hospital rule? Limit x tends to 0, differentiate the numerator. What is the differentiation of the numerator? Numerator differentiation is minus, cos ax differentiation is minus sin ax into a. Cos ax differentiation is minus sin ax into inner function differentiation a divided by, what is the differentiation of x square? X square differentiation is 2x. Now what I am doing, observe here, multiply with a, divide with a. Now here sin theta by theta, sin theta by theta is equals to 1. So we are getting the answer as a square divided by 2. 2. That is the way of proceeding L'Hopital rule. So that is our sin theta by theta, another important derivation in the limits. Now, so I am going to discuss about the Taylor's expansion, which is very helpful for remembering the expansions. Okay, so because in limits, expansions plays a critical role in solving the problems. This is the Taylor's expansion. F of x plus h is equals to f of x plus h by 1 factorial into f dash of x plus h square by 2 factorial into f double dash of x plus h cube by 3 factorial into f triple dash of x plus and so on. That is the Taylor's expansion. Now what I am doing here is put x is equal to 0. If I put x is equal to 0, what happens? F of 0 plus h by 1 factorial into f dash of 0 plus h square by 2 factorial into f double dash of 0 plus h cube by 3 factorial into f triple dash of 0 plus and so on. That is f of h. Now put h is equals to s, then what happens? F of x is equal to h is replaced with x. F of x is equals to f of 0 plus x by 1 factorial into f dash of 0 plus x square by 2 factorial into f double dash of 0 plus x cube by 3 factorial into f triple dash of 0 plus and so on. So with the help of this, you can find out any expansion. Suppose you see, I want to find out the expansion of e power x. F of x is equal to e power x. So can you tell me what is f dash of x? E power x differentiation is e power x. What is f double dash of x? E power x again differentiation is e to the power of x. Now what is f triple dash of x? Again differentiation is e to the power of x. Now tell me, what is f of 0? F of 0 is equals to 1. What is f dash of 0? Is also 1. What is f double dash of 0? 1. F triple dash of 0? 1. Now what the expansion becomes? That means f of x is equal to e power x is equal to f of 0 is 1. F dash of 0 1. F double dash of 0 1. F triple dash of 0 also 1. So we are getting 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus and so on. That is the expansion of e power x. E power x expansion is 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus and so on. Like that you can expand any series. So better to remember these results as the standard results. Sin x is equals to x minus x cube by 3 factorial plus x to the power of 5 divided by 5 factorial minus and so on. That is the expansion of sin x. Yes, you can do with the help of this. At the same time, cos x expansion is 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus and so on. That is the expansion of cos x. At the same time, what is the expansion of tan x? Tan x expansion is x plus x cube divided by 3 plus 2 by 15 into x to the power of 5 plus and so on. That is the expansion of tan x. In a similar way, we have sin inverse x expansion, cos inverse x expansion, tan inverse x expansion also. At the same time, we can remember this particular results. 1 plus x whole to the power of n, which I discussed earlier. 1 plus nx plus n into n minus 1 divided by 2 factorial into x square plus and so on. That is the expansion of 1 plus x whole to the power of n. At the same time, what is the expansion of log of 1 plus x? Log of 1 plus x is equals to x minus x square by 2. Any result we can prove with the help of this expansion f of x is equal to log of 1 plus x is equal to x minus x square by 2 plus x cube by 3 minus x power 4 by 4. Factorial is not there, observe. That is log of 1 plus x expansion. Suppose you want to find out the expansion of log of 1 minus x minus x square by 2 minus x cube by 3 minus x power 4 by 4 and so on. That is the expansion of log of 1 minus x expansion. At the same time, suppose better to know this one also. So because you know this differentiation how to do. So 1 plus x whole to the power of 1 by x expansion is e into 1 minus x by 2 plus 11 by 24 into x square minus and so on. That is the expansion of 1 plus x whole to the power of 1 by x. Better to remember these as standard results for objective exams to solve the limits of problems more comfortably. So now we are going to discuss about the other result. Limit x tends to 0 e to the power of x minus 1 divided by x. So with the help of this particular discussion now, with the help of this particular expansions, we can do this particular one. Otherwise, direct limit substitution, what we are getting? Direct limit substitution, we are getting 0 by 0 form. So that's why we can write Arbitrary rule. Limit x tends to 0, e power x differentiation is e to the power of x by 1. Now apply the limit, because the numerator differentiated, denominator also differentiated. If you apply the limit e power 0, you will get 1. Or otherwise, you know the expansion of e power x, you will get the same answer. Now we can also write limit x tends to 0, a to the power of x minus 1 by x. This also we can do in the same way. So you can apply Arbitrary rule, or otherwise we can write that one as e to the power of x into log a minus 1 divided by x. Nothing here, multiply with the log a, divide with the log a. Now this value is becoming 1, that's why you will get log a. Limit x tends to 0, a power x minus 1 by x is equals to log a. At the same time, limit x tends to 0, logarithm of 1 plus x divided by x is equals to 1. These are some other basic standard results, better to remember. At the same time, another important idea I am going to discuss whenever we are getting in the form of 1 power infinity. How to evaluate the limits when it is in the form of 1 power infinity. Just you can observe here, limit x tends to a f of x whole to the power of g of x. Limit x tends to a f of x whole to the power of g of x. That limit we have to evaluate. Now what I am doing here, observe. Under this condition, that means limit x tends to a f of x is equals to, we are getting 1, and the limit x tends to a g of x is tending to infinity. So in this case we are getting in the form of 1 power infinity. How to evaluate the limits when we are getting in the form of 1 power infinity? So observe here, what we are writing here is, this can be written as e limit x tends to a e to the power of g of x into log f of x. I hope so everyone followed this, because nothing is there, because x power a power, this is e power f of x into log of g of x into log of f of x I written here, right? Now this g of x shifted to the power e to the power of log of f of x whole to the power of g of x. Base is not there, it is natural logarithms, base is e, that's why these two are same. As you know from the logarithms, a power log m to the base a is equals to m. So that's why here base is e, here also e, we can write this one as f of x whole to the power of g of x. So that is the reason the given problem we can express in this way, right? So now I can write this one as e to the power of limit x tends to a g of x into logarithm of 1 plus f of x minus 1 Followed or not? What I did? 1 added, subtracted. Nothing more than that. 1 added, subtracted. You know this information. We know the information is limit x tends to a, f of x value is equals to 1. At the same time, limit x tends to a, g of x is tending to infinity. So now further what I am doing here, observe. Limit x tends e power, limit x tends to a, g of x into their modification you can check. Logarithm of 1 plus f of x minus 1, right? F of x minus 1 divided by f of x minus 1 into f of x minus 1. I hope so everyone followed this one what I did. Multiplied with f of x minus 1 divided with f of x minus 1. Why? You can observe just now we discussed limit x tends to 0, 1 plus log of 1 plus x divided by x. We can write it as 1 because this is tending to 0, this is also tending to 0. Then the value of this limit we can write 1. If you want we can prove as earlier I discussed. With the help of expansion we can prove it this one. With the help of Arbitrary rule also we can prove it. Okay, this one we know that I want to use. The reason is this is tending to 0 because limit x tends to a, f of x is equals to 1. That means minus 1 tending to 0. This is tending to 0. This is tending to 0. That's why this limit value is equals to 1. So now the question changes as e power limit x tends to a, g of x into f of x minus 1. So with the help of this particular results, we are going to evaluate a limit in the form of f of x whole to the power of g of x. Limit x tends to a, f of x whole to the power of g of x. Whenever we are getting in the form of 1 power infinity, we can evaluate like this: e power limit x tends to a power into base minus 1. E power limit x tends to a power into base minus 1. So with the help of this particular result only, we can prove now these particular results. This is one particular question. Limit x tends to 0, 1 plus x whole to the power of 1 by x. Check, we are getting in the form of 1 power infinity or not? Yes, this value is 1 and this value is tending to infinity. So what we can write here, this can be written as e power limit x tends to 0 power into base minus 1. So minus 1 plus 1 cancel, x also cancel. We are getting e to the power of 1, that is equals to e. At the same time, limit x tends to infinity 1 plus 1 by x whole to the power of x. Here also you can observe as x tends to infinity, this value is tending to 0. So 1 power infinity form again. So we can apply e to the power of limit x tends to infinity power into base minus 1. So plus 1 minus 1 cancel, x cancel. Here also you will get e. So you can remember these as standard results, right? So these are the complete ideas regarding the limits. Next class I will try to discuss different levels of questions in limits. Okay, bye bye.